Okay, welcome to 5.2, Evaluating and Graphing Polynomial Functions. Before we do any of that, we need to figure out what a polynomial is. So this is the basic definition where f of x, which is a fancy name for y, is equal to an is just a generic coefficient. X to the n would be the highest degree plus a different coefficient, n minus 1. So an could be 3 and a to the n minus 1 could be negative 2. And then the next degree, if written in standard form, would be just 1 degree lower. And so we carry that on until we get to a1, which again is just another generic name for a number, x to the first, and then plus our a naught, which would be our y-intercept. Without a variable. Okay, the exponents of a polynomial function are always positive and whole numbers. You can just think of it as positive numbers. Always positive whole numbers. So they're not integers, they're not going to be negative, they're just going to be positive. We need to figure out what the degree of a polynomial is. So the degree of a polynomial, that's the label. So people get labeled, unfortunately. Polynomials also get labeled, but for polynomials, it's a good thing. So the degree of the polynomial is the highest exponent. The highest exponent. So if n right here was 10, this polynomial would be degree 10. Okay. And then the leading coefficient, that's another way we classify polynomials. The leading coefficient is just the number in front of the variable with the highest exponent. Number in front of the variable with the highest exponent, or the largest exponent. So for example, if I had f of x equals negative 4x squared plus 10x minus 2, the degree would be 2, which we call that a quadratic. Degree would be 2, and the leading coefficient is negative 4. Right? This is the leading coefficient, and this is the degree of the polynomial. Okay. All right, so we're going to, these are just the most common ones. So the constant is degree 0. Linear, which is an odd degree, which we'll get into that later, but since it's an odd number, is a linear. And here's an example. So 5x, so x to the first would be the highest degree, and 5 would be the leading coefficient. For a quadratic, we'll note that that's an even function because it's degree 2. And so for our example, 2 would be our degree, and also 2 would be our leading coefficient. And then we have a cubic, which I think you can guess that's an odd function because it's degree 3, and 3 is an odd number. So for our example, our degree would be 3, and our leading coefficient is 1. Right? And then we have quartic, which you guessed it, is an even function. And our example is degree 4, and the leading coefficient is 1 again. Okay, so for our very first example, we're going to decide whether the function is a polynomial function, and we're going to write it in standard form, which is the exponents from greatest to least. So for A is already written in standard form because the exponents go from 4, 2 to technically x to the 0. So for part A, we have degree 4, which if it's 4, it's an even number, so would be an even function. And our leading coefficient, which I'm just going to abbreviate as LC, would be positive 1. So just that number in front, technically there's no number, so we call that 1. Part B is not in standard form yet. So we'll put it in standard form, but notice all my exponents are positive. So we have the pi x squared, that would go in front. 7x, there's nothing in front, so that's a positive 7x minus the square root of 3. Okay. Funny coefficients, but still just numbers. So for example B, our degree would be 2, or you could call that a quadratic, and the leading coefficient is pi, which is just a number. We usually abbreviate that as 3.14. And then A and B are both even degrees. C and D are not polynomial functions, so please pause and see if you can figure out why. So for part C, hopefully you guessed it, this exponent is negative, so that is why it's not a polynomial function. For part D, hopefully you picked on this guy, 2 to the x. 2 is not a variable. All of the bases need to be variables, like x squared, x to the 4th. And then x is not a positive / whole number. So this is why it fails as a polynomial function. Okay. All right, for example 2, we're going to use direct substitution to evaluate this. So we are going to put, this is f of 3. These are just directions. That just tells me I'm going to put 3 in for every x I see. So you are going to leave this alone. Okay, don't try to add it, subtract it, anything like that. All right, leave that alone. Those are just directions. And then do yourselves a favor and make parentheses every time you plug a number in before you plug it in. That will cut down on a lot of your little errors that you might make. Okay. So we're going to plug in 3. So please pause the video and see if you arrive at the answer, and then check back with me. Okay. Make sure you're using order of operations. So the first thing we're going to do is exponents before we multiply. So this is going to be 2 times 81 minus 5, and then 3 cubed is 27. Negative 4 times 3 is negative 12 plus 8. So please take your time. 2 times 81 is 162. And then this would be 135 minus 12 plus 8. And then you should get 23. So my directions say if I plugged in 3 for x, I would arrive at 23. And we are done. And that is, we call that substitution. In Algebra 2, we call that direct substitution because we will learn synthetic substitution in a little bit. For your guided practice, 1, 2, and 3 are just like example 1. So one of those is not a polynomial. And then for number 4 and 5, just make sure you make parentheses and just take your time, order of operations. So exponents before you multiply. Okay, now we have example 3, and we are going to use synthetic substitution, which at first pass will be a little bit confusing, but I think once you kind of do it a couple times, you will like it a lot better than direct substitution. So it tells us to use the f of x from example 2, so I will write that down again. So f of x was equal to 2x to the 4th minus 5x cubed minus 4x plus 8. And actually with direct substitution, I'm going to leave a little room, and you'll see why in a minute. So minus 4x plus 8. Okay. If you notice, we don't have an x squared term, so I'm going to just put 0x squared. That will be important for synthetic substitution. So whatever I'm evaluating, I'm kind of going to make a upside down long division box. So I'm going to put that 3 on the outside, and then I'm going to put all my coefficients, including 0, there's going to be 2 rows. So I'm going to put the coefficients on the top row, and it's going to be 2, negative 5. Make sure you put 0. So if your function skipped anything, make sure you have a placeholder for whatever it skipped, and then negative 4 and positive 8. Okay, so now it's kind of like a pinball machine where we're going to drop the 2 outside the box. We're going to start with 2, so make sure you draw that arrow because a lot of people will put 3 accidentally. So drop that 2 in place. These numbers down here, we are going to multiply with 3. So we're going to do 2 times 3 and get 6, and 6 is going to go in the second row in the box. Then we're going to add. So negative 5 plus 6 is positive 1. We're going to multiply again because that's outside the box. So 1 times 3 is 3. We're going to add it. 0 plus 3 is 3. We're going to multiply, and we're going to get 9. We're going to add negative 4 plus 9 and get 5. And then we're going to do 3 times 5 and get 15. We're going to add that and get 23. All right. So again, it's a little weird. We'll do a couple more when we graph these, and I think you'll get the hang of it pretty quick. So if you'll notice, if you look back at example 2, when we plugged in f of 3, we're going to call direct substitution the long way now. When we did that the long way, we also got 23. So synthetic substitution is a very fast way to find values for your polynomial. Okay. This is a little bit confusing, so I'm going to break that down a little bit more. So this slide we're talking about end behavior, but you already know about end behavior, you just didn't know it yet. So end behavior breaks down into even and odd functions. You already know, you've already dealt with in Algebra 1 and Algebra 2 an even function. It's going to be a parabola. And so when you have y equals ax squared plus bx plus c, that's a parabola in standard form. Okay, so with a parabola, you already know if a is positive, you know it's going to go up like a cup. The end behavior that we're talking about is the 2 ends. This is end behavior. So end behavior, they're both going up. If a is negative, you already know from Algebra 1 and Algebra 2 that it's going to go down like a frown. That is the end behavior. That's what we're talking about. So how we apply that to all even functions, because a quadratic is a degree 2, and degree 2 is even. So all even functions have end behavior that behaves this way. So if we had a y equals, let's say, 4x to the 4th plus a bunch of stuff, this would be the leading coefficient is positive. The degree of the polynomial is 4, which is even. So the end behavior for this one is going to go up like a cup. And it might look a little different. It might look like this, but the result is the same. If we had 4x to the 6th, that would also go up like a cup. All right, so when we look back at this very confusing picture, we have degree even. Here's degree even, and leading coefficient is positive. So don't worry about this part, don't worry about that part, but just know that the end behavior, they both go up. And that's just like your parabolas that you've dealt with. If the degree is even and the leading coefficient is negative, then it's going to go down like a frown. So don't worry about that or that, but you know the end behavior is going to go down. Odd behavior, we're going to get there right now. You've already actually dealt with odd behavior in Algebra 1. So if you ever graphed an equation that was y, let's say y equals 3x plus 4, well, the degree of this coefficient, the degree of this polynomial is 1, which makes it an odd function. The leading coefficient is 3, which is positive. And this right here is all you need to know for end behavior. So if we were to graph 3x plus 4, we would start with the y-intercept of 4, and we would go up 3 over 1. We could also go down 3, back 1, and we get this positive slope. Okay? Where the end behavior, right here, it starts low and ends high. Okay? That is what the end behavior is talking about. So if I have something a little bit crazier, like y equals 3x cubed plus 2x squared plus 1, I'm just gonna graph the end behavior correctly. So we still have our leading coefficient is positive 3, our degree is odd. We're still following the end behavior where we're gonna start low. So the odd function, it still starts low. It's going to look a little different in the middle, but it's still starting low and ending high. So it still follows that positive slope behavior, just like it did when in Algebra 1. Okay. If we look at a negative one, let's say we look at y equals negative 1/2 x plus 2, you know how to graph that. Again, our degree for this one, the highest degree is 1, which is odd. And our leading coefficient is negative 1/2, which is negative. Okay. The only thing you need to know for end behavior is if the degree is odd and the leading coefficient is negative or positive. So when we graph this, we start with the y-intercept of 2, and we're going down 1 over 2, down 1 over 2, and we get a negative slope. So see if you can pick out the end behavior. All right, so the end behavior starts high and ends low. Okay. So any odd function is going to follow that pattern. So for example, if we have y equals 3x to the 5th plus 2x squared plus 1, again, I'm just going to graph the end behavior correctly. And then let's change this to a negative so it can follow the same pattern as our example. So our leading degree is 5, which is an odd function, and our leading coefficient is negative 3, which is negative. So it's going to start high. It may do this or this. Again, it follows the same pattern as a negative slope where it starts high and ends low. The middle looks a little different. So when we go back to our lovely key concept box, we're not going to worry about this so much, but if you have a degree that's odd, again, that's x to the first, x cubed, that's the highest degree in that function, and our leading coefficient is positive, it's going to start low and end high. So it's still following that positive slope that you practiced in Algebra 1. If your leading degree is, or your highest degree is odd and your leading coefficient is negative, you're going to start high and end low. So you're still following that negative slope pattern that you did in Algebra 1. So that's what you need to know for end behavior. All right, so this one right here, all right, it looks a little weird in the middle, but our end behavior, they're both going down like a frown. They're down like a frown. The degree is even. Okay, degree even is either it's going to look like this or it's going to look like that, just like you know with parabolas. So automatically A and B are out. And if it's down like a frown, the leading coefficient is negative. So our answer is D. All right, so guided practice, I would use synthetic substitution. So how you get started for number 6 is you're going to put the 2 on the outside. All the coefficients are going to go here. For number 7, you will need a placeholder. So just be careful with that for number 7. Okay. All right, and then now we're going to graph polynomial functions. So now we're actually going to find out some values for those. So when we graph, let's start with A. When we graph A, we're just going to make a list of values. We're going to use -3, -2, -1, 0, 1, 2, and 3. Later in the chapter, we will discover better values to use for x, so don't stress over what values to pick right now. But we're going to use these, and we're just going to plug -3 in, and we're going to use synthetic substitution because it is a lot faster, plus it will give you lots of practice, and you'll be pros at synthetic substitution. Okay. If a friend doesn't know synthetic substitution and they do direct substitution, you could probably bet them that you will find the answer faster and you can win money, all right? Or you can challenge your parents. All right, so let's see, we have no placeholders for A. We will have a placeholder for B, but we're not going there yet. So for A, we're going to use -3 first. Okay, that came from there. We're going to bring down -1 like a pinball. We're going to multiply it and get 3. Add, we get 4. Multiply, and we get -12. Add, we get -9. Multiply, -3 times -9 and get +27. And then we're going to add it and get a +24. So please pause the video and make sure you can do synthetic substitution for the other 6 values. 0, you might not need to do anything, just look at it because the y-intercept is going to be -3. But please pause and do the rest of them and then check back and make sure you get the numbers I get. Okay. So the numbers that I got were 3, -4, 0, -1, and -12. Right, so when I graph that, I'm just going to guesstimate a little bit. So -3 is up here, -2, -1 and -4 is down here. 0, -3 is right about there. 1, 0, 2, -1, and 3, -12. Okay, so let's look at that. What I'm graphing is an odd function and it's negative, so it's going to follow a downhill slope. So when I put the dots together, I'm just going to double check. I started high, which is what I'm supposed to do. Go through all of the points and end low. So my math is right and my end behavior is right. For number 4, let's move that to, or B, let's move that to a different page. So B again was f of x equals x to the 4th minus x cubed minus 4x squared plus 4, right? And for the values, again, please don't stress about the values. For we're just going to use -3, -2, -1, 0, 1, 2, and 3 again, right? So don't worry about coming up with your own x values. Eventually we will have a better plan for that. But for right now, we're going to use these values. So when you set up your synthetic substitution, we'll just start with -3. We're going to put -3 on the outside, and we do need a placeholder. So we have 1, -1, -4, 0, because there's no x term. That's 0x, and then 4. So we're going to bring down the 1 again. That's kind of like the pinball. And then we're going to multiply and get -3, add to get -4, multiply -4 and -3 and get +12. Add them and we get 8, multiply, we get -24. We add them, 0 plus -24 is -24. And then we're going to multiply. We're going to get 72. Oops. +72. And when we add, we get 76. So this will be 76. So please pause and find the rest of the values and then check back with me. And the values you should hopefully get are 12, 2, 4, 0, -4, and 22. So before we graph it, let's look at what kind of degree we have. The highest degree is 4, so that would be an even function. And there's nothing out in front, so that would be a +1. So even positive is going to go up like a cup. So before you start graphing the points, just check and make sure you know what the end behavior is, because that's probably the newest thing in this section. So when we graph this, -376, -212, -1, 2, 0, 4, 1, 0, 2, -4, and 322. Okay, so when I connect the dots, again, it looks a little weird in the middle, but my end behavior, they're both up like a cup, which is what I wanted. Okay. All right, so example 6, please read this and figure out what's going on. Pause the video. All right. Okay, so we're trying to figure out, we're going to graph this. So S is our X value and E is kind of like the Y. So here's the one they gave us. All right, so again, don't worry about the values. The values are 10, 20, 30, and 40. So, which I forgot 20. Okay, 20, 30, and 40. There we go. All right, so pause the video and make sure you can find those values, and then make sure you do the exponent first and then multiply. But you should get 0, 29, 464, 2,349, 7,424. So when we graph that, we're not really worried about negative wind energy. So what we're going to do is we're just going to have just quadrant 1 when we graph. And I'm going to make this 0, 10, 20, 30, and 40. And then over here, I'm just going to have 1,000, 2,000, 3,000. So notice I'm not going all the way up to 7,424 because we just need to we need to use the graph to generate what 1,000 foot-pounds of energy will do. So here's our wind, and then here's the energy part. So 0, 0, 10 is 29, so maybe right about there. 20 is about halfway up between 1,000. 30 is a little above 2,000, and our 40 is above the graph. So here's our graph of that function. And then to find 1,000 foot-pounds, here's my 1,000 foot-pounds of energy. So I'm just going to go here, find where it intersects, and it looks like it's about 24, 25. So about 24 knots to get our 1,000 foot-pounds of energy. Okay. The guided practice, let's see, number 9, 10, and 11. So number 9, make sure you have a placeholder for x cubed, and you're using the same values that we did in the example. Number 10, you don't need a placeholder, but use those same x values. Number 11, we need to rewrite this in standard form. So we have negative 2x cubed plus 4. And when you set up your synthetic substitution for number 11, you're going to have a couple placeholders. So we have the x cubed, 0x squared, 0x, and then 4. And then use those same x values we did on the example. For number 12, again, you're going to do the same exact thing. So for your s values, just please use 0, 10, 20, 30, and 40. And that will be the end of the lesson today.